Today we are going to discuss motional EMF. What is motional EMF? How it is generated? What is the expression for it? And we'll discuss what other things we can get from this expression. Different forms of it, different information what we can get from the concept of motional EMF. We'll also discuss a case when a rod is being rotated about one of its ends in a uniform magnetic field. What is the expression for the EMF generated across its ends? And we'll discuss many cases related with this and the different things what we can get from that, what type of questions that can be asked on this particular topic. So all these we'll discuss in today's discussion. Motional EMF is the EMF generated across the ends of a rod which is moved in a uniform magnetic field or in a region of magnetic field. We'll first of all see how it is generated, and then we'll do what will be the expression for this EMF. Suppose there is a region in which there is a uniform magnetic field B, and its direction is, say, it is into the plane of the board. So this is the region in which we have the magnetic field B there. Here we have, suppose, a rod, and this rod is being moved in this region. Say it is being moved from left to right. Suppose this end we call it as P and this end is Q. If this is a conducting rod, in that case, it will have the free electrons. So the free electrons, as the rod is being moved, they are also in motion. So they will move in the direction of the motion of the rod. So now you have free electrons, suppose, moving in this direction. Magnetic field is directed into the plane. So they will experience a force. They will experience force due to this magnetic field. And we can easily find its direction by using a right hand screw rule there or right hand thumb rule there. So here, suppose if you consider that the velocity is in this direction, magnetic field is directed into the plane. So in that case, from velocity to magnetic field direction motion, if you are considering, in that case, you'll find that as the velocity is in this direction, magnetic field is into the plane. So their motion will indicate that there will be a force on the charge, if it is positive, in a direction Q to P. Because magnetic field is into the plane, velocity is in this direction. So the direction of force, if you are considering, in that case, it will be directed Q to P. But since you have the electron here, so they will be experiencing a force in a direction P to Q. And what will be the magnitude of the force that you can easily get? That the force will be equals to EVB sine theta, and this is your sine 90. So this is your EVB. This is the force due to magnetic field. So what will happen? These free electrons will move towards the end Q. Now, as these free electrons are moving towards this end, obviously there will be positive charges developed at the other end. And if now there is accumulation of the charges there, in that case there will be a field setup due to this accumulation of the charges there, and this one will be, here it is positive charges induced, here is the negative charges which are developed there. So they will set up a field there. As a result, now if you consider for the electrons which are there, they will be experiencing force in this direction. This is the direction of, say, force due to magnetic field, which is your EVB, and there will be force due to this field which is set up there. So that force will be given as your E into capital E. This is the force due to electric field. So this is your E into capital E. Now the moment these two will exert equal amount of force, in that case the further movement of these charges will be stopped. Because with the accumulation of more and more charges there, their field is getting increased there. So what will happen, that in equilibrium, when you have these two forces balancing each other, so you have F QE equals to QVB, or E we can take as VB. This is happening when force due to electric field is same as force due to magnetic field. Okay, so we have this relation. Now, as there is an electric field set up, what will happen? There will be definitely a potential difference between the ends of the two, and that potential difference we can get if suppose you have this rod of length L. Due to this electric field which is set up there, there is a potential difference between these two ends. And that potential difference, if you consider as capital V, this will be given as your E into L. Because you know that E is equals to minus del V by del R. So taking help of that, we can write that if the potential difference, which we are representing it as V, and its length is suppose L, in that case it is can be written as your E as V by L. Remember, this is the potential difference. So obviously V we can write as E into L. So this is your E into L, and that can be written as your, for E we are writing V into B, so it is your V into B into L. So this is the potential difference. This is the potential difference developed across the ends of this rod. Or you can say that it is also the EMF generated there. So it will be the EMF generated across the ends there of this rod. If this rod, because it is not a closed circuit, if you connect it with a conducting wire there, so that there is a complete circuit there or closed circuit there, in that case there is a flow of the charge there. So there will be flow of electric current there in the circuit. So this value of potential difference, we can show that it is V equals to small v dl, where this V is the velocity with which this conductor is moving there, B is the magnetic field, and L is the length of this conductor. So this is the expression for the motional EMF, which is developed across the ends of a rod there. Why we are saying motional EMF? Because this is due to the motion of the rod in the region of the magnetic field. So the EMF which is generated, that we take it as BVL, or this is your VBL there. There is another way in which we can get the expression for this motional EMF there. In this case, what we are assuming that again here we have a region of the magnetic field which is directed into the plane of the board. So this is the magnetic field directed into the plane, and suppose this is being represented as B. We have a U-shaped track. This one like P, Q, R, S. This is representing a U-shaped track. These two are the parallel one, and this is the one which is connecting these two parallel tracks. We have a slider MN, which can slide over this parallel track. Now here, if this end is at a distance x, suppose, that is, this Mn at any particular position is at a distance x, and the distance between the parallel tracks is your L. That can also be said that this is also the length of this rod Mn. So here, for this particular case, magnetic flux, which is enclosed by this closed loop, that is your MNRQ. So magnetic flux linked with closed loop. This is your BL into X, because it is your B into A into cos theta. So it is your BL into X. Angle between the magnetic field and the vector area, it is 0 there, or 180, whatever you can take. So this is your BL into X. Suppose the slider is moved through a distance dx. So if I suppose exert some force and it is being moved, in that case, the new flux associated suppose the slider is moved through delta x. So the new flux associated will be equals to BL x plus delta x. This is the new flux there. So the change in flux this is your BLX plus delta x minus BLX, which is equal to BL delta x. This is the change in the flux. And suppose this change happens in time delta t. So delta t be the time in which this flux change takes place. So what will happen? Rate of change of the flux. So the rate of change of the flux will be delta phi by delta t, limit delta t tending to 0. So that means this we can write it as your BL delta x by delta t, limit delta t tends to 0. Now this particular term, delta x by delta t, where limit delta t is tending to 0 is v, that is the velocity with which it is moving. So in that case, the rate of change of the flux, it is your BLX. And by Faraday's law, what we know that now as E magnitude wise, it is your rate of change of flux. So E will be equals to BL. This is the expression for EMF developed across the ends of this rod Mn when it is moving with velocity v in the region of magnetic field T. So this is the expression for the EMF, that is your BLV. We can get the same expression for the EMF developed across the ends of this rod by taking just the flux and differentiating it with respect to time. So as we have phi equals to BLX, magnetic flux associated with this closed loop is your BLX. So if you differentiate it with respect to t, with respect to time we are differentiating. So in that case it is your d phi by dt, which is your BL dx by dt, and dx by dt will give you the rate at which this rod is being moved. Suppose it is being represented as v. So in that case this will be equals to BLV. This is the d phi by dt. Now we know from Faraday's law that magnitude of E is equals to d phi by dt. So this is your BLV. So the EMF developed will be equal to BLV. This is basically the magnitude of the EMF developed. So this is how we can get the expression for the EMF developed across the ends of this rod. There can be a number of questions which can be framed on this setup there. So suppose it is given that this is the parallel track, U-shaped parallel track kept in the region of the magnetic field. Magnetic field strength, we are taking it as B. And this is suppose your AB, CT. This is the slider. Now we have seen that EMF generated or the potential difference developed across the ends of this rod if it is of length L. This is given as your E equals to BLV. Suppose you want to know what is the current developed. So suppose resistance of this circuit, if I assume that here we have a resistance R. So let R be the resistance, of the circuit. So in that case, the current which is developed, I, this is your E by R. So suppose I want to know what is the current there in this one. In that case, it is your I. So this is your BLV by R. This is the expression for the current which is developed or induced in this closed circuit. Now, if the magnetic field is directed into the plane and the slider is moving in this direction, so the flux is increasing. If the flux is increasing, the direction of the induced current according to Lenz's law should be in such a direction that it should oppose the cause which is producing it. So the cause is increase of the magnetic flux. So it should set up a field in opposite direction to this one. So this should set up a current there in this loop in the anti-clockwise direction, so that the field developed by that will be out of the plane, which is opposite to this field which is already present there. So the current will be in the anti-clockwise direction. And this is the expression for the current there. Now, if here we have seen that we have the conductor, say PQ of length L, it is moving in the region of magnetic field. EMF developed we have obtained. Now we have seen that it will have the current there because it is a closed loop there. And if it is a closed loop and the current I is flowing, definitely it will experience force. So the force which is experienced, this is given as your ILB, sign of the angle between the current and the magnetic field there. So in that case, this one will be again 90 degree. So in that case, this is your ILB, and I we can write it as your BLV by R into LB. So the expression for the force will be B square L square V by R. So this is the expression for the force on this conductor or rod which is of length L and is moving in the region of the magnetic field. Now, once we have got the expression for the force, we can also find out what is the power developed there, or what is the power developed in this particular circuit. So the power developed, this one we can get it from force and velocity product. Force into velocity will give the power developed. So in this case, this is your B square L square V by R into this V. So this is your B square L square V square by R. This is the expression for the power developed. So this is the expression for the current induced or current developed. This is the expression for the force which is developed on this conductor there. which is moving. So in this case, the force on this one will be given by the expression B square L square P by R. Power developed will have this expression. There can be number of variation in this type of question. So far we have assumed that these parallel tracks does not have any resistance. They are just a conducting track which do not have any resistance there. But if I assume that these parallel tracks have some resistance, in that case we'll have to consider the expression for the resistance which is now there in the closed circuit. So if you want there, in that case we can find out what will be the resistance of this circuit there. Let's take the case if these parallel tracks have some resistance. So far we have assumed that they do not have any resistance, they are just the conducting tracks there. So when parallel tracks have some resistance, so in that case we are assuming that let lambda be resistance per unit length of the tracks. So it is the lambda. So now if I assume that this is at a distance x, so when the slider is at distance x, at a distance x from one closed end, in that case resistance offered by parallel tracks, this will be how much? This will be lambda into x by each, and since these are the two, so it is 2 times lambda into x. So now the effective resistance, because this resistance is also there, so if I assume that this is the resistance between the parallel tracks, these lambda x is the resistance of these parallel tracks there. So in that case, effective resistance of the closed circuit will be equals to R plus 2 times lambda x. So now in this case, current developed which we are taking as E by R effective. So this time it will be how much? It will be your BLV divided by R plus 2 times lambda x. So this is the expression for the current developed. Similarly, if you want to find what is the force on the slider there, so in that case now this is the expression for the current. So now if you have to find the force, it is your ILB. Now for I will be taking this expression. If you have to find the expression for the power, in that case it will be multiplied by the velocity term there. So accordingly you can make a change. Now let's assume a case when this particular slider PQ also have some resistance. So let R naught be resistance of slider PQ. So in that case what will happen? So there will be some resistance of this part. There is the EMF developed. Best is that you assume, like here we are assuming that it is R naught there. What is the EMF developed? That is your E. You can treat this one like a cell. This is the cell of EMF E. This is basically this PQ. It's in place of internal resistance, you just assume the resistance of this rod PQ. So it is your R naught. And what is the resistance next connected to this one? If I assume that this is R as the resistance between the parallel tracks. If the resistance of the sliders are, if the resistance of the tracks are also given, that they have some resistance, so in that case it is your 2 times lambda into x. Now we can find the expression for the current there. And here you can also find what will be the net potential difference in this case. If this slider has some resistance, it is just like the potential difference across the terminals of a cell when it has some resistance there. So that concept you can use if this slider also has some resistance. Best part will be you just assume it like a cell with some internal resistance. This E is your basically BLV and this R0 is its resistance. And now it is the resistance of the external circuit there. What we are taking it as your R plus 2 times lambda x. So you can get the desired things there, what has been asked in the question, and you can take help of this expression. There are a number of conceptual type questions based on this motional EMF. You may be given that a rod is being moved with this particular velocity in the region of magnetic field. Then what is the EMF developed across the ends? That we can easily get from the formula. But depending upon the situation, depending upon the given conditions of the problem, you will have to see what EMF is basically getting developed. What is the expression for the magnetic field there, what we are taking. So best will be there. You see that which lines of forces, magnetic lines of forces is being cut by the rod. Like suppose if it is given that we have a rod which is being moved horizontally and it is the Earth's magnetic field. So if a rod is moving horizontally, in that case, which magnetic lines of forces it will cover? Because at any particular place, you have the Earth's magnetic field there. If angle of dip is there, in that case, you can easily find what is the horizontal component, what is the vertical component there. So if a rod is being moved horizontally there, in that case, suppose it is moving in the north-south direction. So if a rod is being moved in the north-south direction there, so it will be basically cutting the vertical magnetic lines of forces. So the expression which you are using, that is your BLV. B there will be the vertical component of the Earth's magnetic field. That you will have to consider. So in that case, it is the vertical component of the Earth's magnetic field. But suppose it is said that we have a rod and it is kept horizontally. Say it is in the east-west direction and it is being dropped. So if it is kept in the east-west direction there and it is being dropped there, in that case, what will happen? You have in the north to south direction Earth's magnetic field, that is the horizontal component of the Earth's magnetic field. So if the rod is falling in the east to west direction, say it is falling in this direction there and it is falling horizontally there, in that case it will be cutting these horizontal component of the Earth's magnetic field. Because you can treat it like this. Suppose this is your Earth's magnetic field, that is the horizontal component of the Earth's magnetic field we are taking. And this one is falling in the east-west direction. That means it is falling like this, being kept horizontally. So it will be basically cutting these magnetic lines of forces which are basically in the horizontal direction in the north-south direction of the Earth. Because then it will be perpendicular to that. So there it will be the horizontal component of the Earth's magnetic field. But the same rod, if it is kept in the north-south direction and it is being dropped, it is falling now in this direction. That is, it is kept in the north-south direction and now it is falling there. So as it is falling horizontally, first of all, it is not going to cut the vertical magnetic lines of forces. Second thing is there that magnetic lines of forces are there, say north-south direction, and it is also falling in the north-south direction. So this is not going to cut even the horizontal component of Earth's magnetic field. So in that case, no EMF will be developed across the ends of this rod. So very minutely you see in the question what is given, how the body is moving, what is its orientation. With that, you will be able to know which component of the Earth's magnetic field it is going to cut. That means the magnetic lines of forces they are associated with that. And accordingly, you can find what is the EMF developed. In the same way, suppose I take a rod, it is kept vertically like this, and it is dropped also, so that it is falling vertically along its length. So if it is falling like this, it is not going to cut any horizontal component because it will be just grazing there. Vertical magnetic lines of forces also it will not cut because it is falling parallel to it. So no EMF will be developed across this rod. So never try to attempt problems where the rod of length L is given and it is moving with velocity v. The region of the magnetic field has this particular value of magnetic field. Also see how it is oriented, because then only you will be able to get the expression for the magnetic field there, that which will be encountered by this rod, and then correspondingly you can find what is the EMF developed. In the same way, you will find very common question there. We have an aeroplane moving with this particular velocity, and it is moving in the region where the magnetic field has this particular value and angle of dip has this value. Say angle of dip is suppose given 30 degrees, 60 degrees, Earth's magnetic field at that place is given, and the plane is moving in the horizontal direction there with this particular speed. So first of all, you see that if it is moving horizontally, in that case it will is going to cut the vertical component. So if B is the magnetic field at a particular place, angle of dip is delta, horizontal component is BH, vertical component is BV. So when it is moving horizontally there, in that case it is going to cut the vertical component of the Earth's magnetic field lines. So in that case you will find out with the given value of B and delta what is the vertical component. And in that case you will get the expression for the EMF developed where you are using BLV. So don't just put the value of the magnetic field here. In this case, it will be the vertical component of the Earth's magnetic field which you have to take care. And that you have to substitute. So in such type of problem, very minutely check what is given in the problem, how the body is moving, and then visualize which particular lines of forces there it is going to cut. And then you will get the correct value of the EMF developed. Let's now take a case for the EMF developed across the ends of a rotating conducting rod. Like here, you have suppose a rod, and this is suppose the rod of length L, and it is being rotated about one of its end. One end is fixed and it is being rotated about the other one. Rotated like this with the angular speed omega, and it is there in a region of magnetic field B. Suppose B is the region of the magnetic field, and this rod has the length suppose L. This end is fixed. So if you have to find out what is the EMF developed across the ends of this rod, now you can see as it is rotating with one end being fixed. Earlier case what we have done? We have done the case when the rod is moving there along its entire length there, it is crossing there in the given region of the magnetic field. Here it is rotating in the region of the magnetic field. So in this case, what we can take, as it is moving, In that case, it will cut these magnetic lines of forces which is there by its length. So suppose we take an element which is at a distance x from it and its length is suppose dx. We have an elementary section of the conductor at a distance x and its length is suppose dx. So here, whatever velocity it will be developed, because it is rotating with a particular angular speed, suppose omega, in that case, this one will have some velocity. Suppose it is your v. So velocity of this elementary section, so velocity of elementary section, this is your v, and this v will be how much? Because we are using the formula v equals to r omega. So this v will be equals to x into omega. Because here it is at a distance x. So this particular element which is here, if you consider the formula v equals to r omega, it is at a distance x. So it is x and angular speed is omega for the entire rod there. So it is your omega. So v will be equals to x into omega. Now this has a length dx. So the elementary EMF developed, or the EMF developed across the ends of this rod of length dx, which is now moving in the region of magnetic field with velocity v. This will be, so EMF developed across the elementary section. This EMF developed across this elementary section, this is your B. What is V? This is your x into omega, and its length, it is your dx. So this is the EMF developed across this elementary section of length dx. So total EMF developed across the entire rod. That will be the integral of this quantity. So it is your dx omega dx integral, and integral will be from 0 to L, because its length we are assuming it is L. So it is this integral, and this is equals to your b omega x square by 2, 0 to L, and that is your b omega by 2 L square minus 0, or that is equals to b omega L square by 2. So this is expression for the EMF developed, or the potential difference developed across the length. This is the expression for the EMF developed across the ends of this particular rod, or the potential difference developed across the ends of the rod, which is being rotated in the region of magnetic field B, when one end of it is fixed and it is rotated with the constant angular speed omega. So this is the expression for the EMF developed. Based on this, you can get another type of questions where it will be said that we have a wheel, and this wheel has a number of spokes. And this wheel is there in the region of the magnetic field. It is suppose B. And the spoke's length is L. And this is being rotated with the angular speed omega. It is just like earlier what we have done. We have taken a rod, and we have taken that the rod has one end being fixed, and it is being rotated about that fixed end in the region of the magnetic field with a particular angular speed omega. We have seen what is the EMF developed across its ends. And we have got the expression for the EMF developed as your B omega L square by 2. Now, if you consider a wheel with a number of spokes, so in that case, so many number of the spokes, which are like now the new rods there, they are rotating. So in that case, what is the EMF developed across its center, that is the center of the wheel, and a point on its circumference there, or the rim of the wheel, you can say. Let there be n spokes of the wheel. Okay, so in that case, if there are n spokes, what is the EMF now between a point at the center and the point on its rim? Here the students get confused because they consider that each will have the same EMF E, and there are n spokes, so net EMF will be n times E. But that is not correct. If you just look slightly cautiously here, if we consider that if this is one particular spoke and it has length L, it is rotating with angular speed omega, and E is the EMF developed, I can treat it as if it is like a cell here whose EMF is E. Other one also we can treat it like the cell of EMF E. Others also. So we can treat as if we have the cells there. So each spoke now we can represent as having an equivalent cell there. So they all have the cell. We can assume that as if the cells are there of EMF E, which is connected. Now you just look at the diagram, how the cells are connected here. You can consider that they all have the positive terminal connected at one point O. So this is suppose one cell, this is another one, this is the third one. They all have their positive terminal connected at one point, whereas the negative one is connected to the point on the rim. So in that case, their other end is also connected at other point there. If E is the EMF, how the cells are connected? They are in parallel. So if they are in parallel, obviously what will be the net EMF? It will be E. That simply means the EMF in this particular case also, when there are n spokes, in that case the net EMF will be equals to E omega, which is your B omega L square by 2. So this is the net EMF there. Now again, here also you can consider that means it is not depending upon the number of spokes. So if it is not depending upon the number of spokes, whether it is a single spoke or double, n number of spokes are there, it is the same value of the EMF. But one more conclusion we can draw from this. If suppose you assume that there is no effect of increase or decrease of number of spokes there, if you go on increasing the number of spokes, what figure will ultimately get? Will get a disk. So even if now we assume that you have a disk which is rotating with the angular speed omega there, and the disk has the radius L, the same value of EMF will be there across the center and a point on the circumference of the disk. So EMF across the center and a point on its circumference of a disk, that is also your B omega L square by 2. Because if it is not depending upon the number of spokes, if you are going and increasing the number of spokes there, ultimate shape will be like a disk. So there it is the same value of the EMF developed. Now here you may think that if it is a solid disk and if it is rotating, the magnetic flux linked with that disk will be how much? It is B into pi r square if r is the radius of the disk. So if that one is rotating, in that case the flux is not changing. So flux linked with that disk, it appears that it is constant, but the number of magnetic lines of forces will be definitely encountered by that disk, which we can assume as if it is made of number of small strips there, which is rotating. And if they are rotating there with the different, with the angular speed omega there, they are cutting the magnetic lines of forces, which is normal to the surface of that disk. So then there will be the EMF carried out. So you can get a number of questions there based on this. So you just read the question carefully and then try to answer.